Hey everybody, figured I'd go live. We are going to try out a couple of things here. These are two topology optimized uh, bottle openers for practical use, and the idea tonight is to see if we can sinter this. This is 17.4 steel filament from the virtual foundry. These are two identical parts aside from a few over extrusions on this one, but identical otherwise. We're going to see, have a baseline if the copper putty infiltration will work for one, and baseline, perfect, train. uh, Anyway, baseline will be just the standard debind and sinter phase. What we're going to try though is a low temp, higher hold at peak time to see if we can get this to sinter. It's difficult to try these experiments one-offs because generally they take a couple hours to print. There's preparation time, and then you have to debind and sinter, which can take anywhere from 10 to 15 hours depending on the cycle. So we're trying to do both at the same time with these, and I'll just walk through that process and hopefully have some success at the end. For anyone watching, no, you won't see the end result in this video. That'll be posted later on due to the timing. So let's get started. Cheers. I keep the copper putty in the freezer just so it doesn't dry out, and in a Ziploc. All right, so let's go ahead and lay our first layer of ballast down. This is a alumina ballast. There is some mixture of graphite in here because we're working with steel, so that will help during the sintering process. Normally during my videos I would edit this out, but now that this is live, you get to see how long this actually takes. Which really isn't bad considering casting takes quite a while for mold prep, and anyone on YouTube would generally edit that kind of stuff out. So let's go ahead and give this a shake. We're just going to level out the ballast here so that we have a nice bed for our part to sit on. Also, I didn't make these bottle openers. They were on Thingiverse. Once this video is uploaded, I'll add the link to it. So the way I'll identify the base test part is we'll just put it near the back, and this back end will go towards the end of the kiln. So I'm just going to go ahead and press that in now, since there's nothing to really do here for the base part, testing part. And we'll shake that so we get it in every crevice. The ballast is used for supporting, so something like that, supporting the part during the sinter step. Sintering just meaning that you're fusing the metal particles so that they're solid. Okay, there we go. And generally during the with this process, as you can see, we were able to just go ahead and print the part already optimized. There's nothing that has to be done. With casting, you'd probably be worried about some of the thinner areas actually filling out, so the mold actually might be difficult here. Or with machining, you'd actually just waste every gap here because you'd have to start with a solid chunk of metal sheet to get this shape. So anyway, so this is our base part, and again, it'll be at the top, and we'll go ahead and prep for the copper putty. Liquid phase. I'm going to go ahead and get gloves for this. This gets a little messy since I probably have to reconstitute some of these chunks here. They're frozen, and I need them to be more malleable so that we apply a good layer on top. Now, the idea behind this is that we apply a layer of alloying metal that during the sinter step will actually get sucked into the part. This being powder metallurgy, there's air gaps between the metal particles, so the alloying metal will actually get sucked into this structure during the high temp sintering phase, and sort of solidify it. It kind of sucks it up through kind of like a straw. So anyway, that's the idea. The metal that I'm alloying with is copper, and the reason that I picked copper is due to its relative melting point to the sintering temperature of the steel. The steel that I'm going to be doing here is 17.4. We're going to be sintering it at a lower temperature, but still very high. It's about sintering it around 2040 degrees Fahrenheit, and the melting point of copper is below that. So the idea is that will get sucked into this part, solidify it, and make it very strong, but sort of like an alloy. Anyway, let's go ahead and get that prepped. So we'll be wearing gloves for this part. Again, it is a little messy due to the components. Alright. So I'm kind of eyeballing this. I don't have an exact science for the ratio of putty to part. This is again sort of a science experiment to try a base part without any copper putty and one with copper putty to see if there's actually any benefit to this. This is something I've made here and nothing that's been perfected. So now that that's out of the way, we'll go ahead and just kind of eyeball it. I'm thinking something about yay big, and we'll mix that up. I'm just going to use some ethyl alcohol. You could probably use isopropyl as well. I have ethyl. This is a little safer for skin, but they're both pretty equivalent. So let's get that. And again, looks good enough. So we'll mix some of that up. You can't really overdo it. If you do, the process would just be to kind of machine that down. If it's not enough, then it just won't work as good. So we'll go ahead and mix this up with just a little bit of ethyl. Let's see, what can I mix this with? I have a wooden dowel. Go ahead and just try to mix that up into more of a paste to apply. This was frozen. And also, before I forget, I'm going to just go ahead and seal up the rest of this. So we'll just mix this up. And as you can see, it's kind of getting into a very black slurry. This was formulated kind of to target the properties of steel. So there is some graphite in here already, as well as in the refractory, and graphite is going to help during the sintering step to kind of pull out some of those impurities. All right, here we go. So this is looking pretty good. I don't know if you can see that. Kind of just looks like black tar on the preview, but it looks more like pudding. Okay, you just don't want to eat that. All right, so we have that mixed up, and what I'm going to do is lay down a shop towel, napkin, whatever you want to call it. Get this. We don't want this all over the bench. Not that it really matters. It's a workbench. All right, so let's see. Good way to apply this. I could just scoop it on, but that might be messy. I think I'm going to get a paintbrush and just a small one and apply this kind of gradually. So just get a small paintbrush, mix this up one more time. The ethyl alcohol will actually evaporate, and I'm kind of hoping that it does fairly quickly to dry into more of that hardened shell. But let's go ahead and paint this on. So I'm just going to pretty liberally apply this to the surface. And again, this is copper putty, which I have made in-house for the purpose of trying to alloy this copper and see if we get a stronger part in the end result. And this should dry pretty quickly. I'm not going to be too worried about it drying before I place it into the ballast, because during the debind stage, we actually ramp up to pretty slowly to a... Okay, this is looking pretty good. Pretty slowly to a pretty good temperature to burn out the PLA binder, or I should say PLA equivalent binder in Virtual Foundry's filament. So that really should dry it out and kind of get it settled onto the surface. Okay. And one thing that I'll mention that I'm doing differently than for any previous viewers, one thing I'm doing differently is increasing the peak temperature of my debind, or sorry, not debind, the sinter cycle, because my kiln actually was advertised to be able to get up to about 2,400 degrees Fahrenheit, and it seems to be maxing out around 2040, which is a big gap. Certainly not salty about that at all. But we're trying to work around that. I don't want to have to buy a new kiln. This was a good price for the kiln. I got everything for a little less than $1,000 for the kiln and the controller and everything. And ideally, I'd like to keep using it. It's got a great build volume, not build volume, thinking 3D printers. It's got a great just kiln volume in general, and it works on 120, which for me that's perfect. I don't have a lot of extra slots for the power, so just a hobbyist in the garage making metal stuff. Maker-friendly gear is very welcomed, but we're trying to get around the limitations that the kiln is presenting. Anyone else with a kiln that can actually get up to about 2250 to 2300 degrees Fahrenheit probably wouldn't have any of the problems I've had with the steel filament. I've been able to sinter copper, really great, and that would apply to bronze or any of the lower melting temp metals as well. So I'll have a link to the kiln in my description. I've already done a video on some of my equipment, but can't hurt to put it twice. So again, for anyone just joining, just painting on some of this putty. I'm about done. It's about covered. I'll probably do another layer on. This is primarily copper, which is used to alloy into the 17.4 steel filament. And it also, I'm in dire need of a sip. Okay, so this is to alloy into the steel filament to produce a less porous part and actually stronger in the end. So we've kind of eyeballed the ratio of the putty, because that's what we do in the garage workshop. But hopefully this method of applying it just to the surface where it's soaking in should produce a pretty even coat. So I'm going to do one more coat just on the top to finish up the material here. And we should be good to place this in with our baseline steel part. Again, thankfully, due to the benefit of the kiln, we have a pretty large volume and are able to use these large alumina crucibles, which let us sinter. This is probably 7 to 8 inches, in the X and Y. It's only a few inches, probably 4 to 5 in the Z, but the kiln itself can hold a lot larger than that. I've made 7 cubed and could go a little higher than that if we add a probably about 8 due to the shape of the kiln. It's sort of house shaped. I'm lacking the word for that right now, but anyway, we'll finish this up here and put it next to the base part, which is going to be our control. And we're again doing sort of 2 experiments in one to save some time, since we only have 1 kiln in the shop. These experiments generally take about 2 days with printing, debind, sinter, post-process. So trying to optimize the amount of parts that can go in at one time is pretty critical for testing out some theories for this. This is looking just about saturated. Alright, so I'm going to just call it at that. That looks about as much as we can handle on this piece. And just so that anyone new is watching can see what we're doing here, we have our control piece, 17.4 virtual foundry filament. That's going to be at the top. We're going to put the coated piece down at the bottom so that we know, which one is what, and we'll be able to measure the changes. The liquid phase sintering should actually reduce the shrinkage, increase the strength, and decrease the porosity of the final part. Not only that, it should actually, to my benefit, lower the temperature at which I need to achieve for my kiln, because copper melts at a lower temperature and should be absorbed into this to this part. At least that's the theory. Should be absorbed into that part at around the melting point of copper. So even though my kiln can't reach the 2400 degrees or 2300 degrees that's necessary for steel, we're going to try that here. But for the base part, we're actually looking to see if a lower temperature sinter can work at all, which, based on the research, we should be able to get. It's just hard to prove out. So what I've done for the kiln cycle, for the burnout, is increase the peak hold time at 2025 to 2040 instead of 2.5 hour hold time to about 5 hour hold time. So that's going to mean that we're going to have to increase the carbon level that this is going to hold. So reduce the ballast, increase carbon, place lid, and hopefully that doesn't burn out, because the idea is that we want to scavenge all of the oxygen that can get to this part to oxidize it. So anyway, enough of me rambling. I will go ahead and place this part. That probably gave it enough time to dry out. This is the final, we're missing a little bit. My OCD is telling me I can't put this in until this last little bit's covered. Let's go ahead and put that in there. Okay, looking a little better. So we'll orient the part the exact same way into the crucible. I gently press down into the first layer of the ballast, and this ballast is alumina with some silicon dioxide, I believe, if I'm not speaking out of my ass, and with some graphite. Graphite's only needed for the steel. So we've pressed these both down and oriented them in the exact same way. I will go ahead and give this one final shake to make sure that the part is well supported. The control part seems to have good coverage throughout everywhere. The part that I just painted is probably a little lacking in some of the crevices, but that's not all I'm testing here. So go ahead and take these off. Don't need sweaty hands for the rest of this. And we'll switch to the regular old shop gloves. Alrighty. Now, the next step that I will be doing is covering the top layer with remaining ballast. Again, this is the exact same stuff that the first layer is holding. I'll just use some regular old measuring cups for this. Nothing special. I'll generally apply this. I want to kind of even this out if I can for the first layer, but I'm going to be doing some shaking and some tamping down. Some tamping down so that we make sure that we have very good support on the part. So this will go a couple layers deep. And for anyone wondering, this ballast can be reused indefinitely. I have not had any need to throw this away throughout over a year and a half of sintering. I bought this stuff off Amazon, but you can buy this off the Virtual Foundry website too. It's the same stuff, same-ish stuff. Let's see. Okay, yeah. So one-time investment, you can get infinite use out of this almost. Alright, so first couple of layers, I will shake this and try to show that it's actually pretty powdery. And we do this to fill in any of the gaps that the part has. This part's a pretty relatively easy shape, so I'm not worried too much about support. There are some more complicated shapes, which you kind of have to do a few special things just to make sure that all the crevices are supported. But that's not what we're doing today. Okay, so I'm going to put just a couple more scoops. All that you really want is for the part to be covered. You want it to be supported because during the center step, it gets very, very close to melting, but it's not melting. So it's sort of liquidish-y, and it fuses together, and the ballast supports it and holds it in place, but it doesn't melt altogether to lose shape. If you to go past the melting point, a lot of people you'll find that you'll see some edges losing definition, or just the part totally washed out, and that's not what we're trying to do. In fact, I can't do that with steel because my kiln can't get up to the temperatures for that. So I really don't have to worry about that here. I just wanted to make sure that everyone was aware of what we're trying to do here. So that is looking pretty good. We are about halfway up the crucible's edge, which is nice because for this I need to introduce a lot more carbon so that I ensure that it does not run out during the sintering cycle. I've increased my temperature, the peak, to 5 hours instead of 2.5. So that means that's 2.5 more hours that this has to burn off, can't scavenge if it runs out, and oxidizes my part. 2 parts. So ideally, I want to just cover this to the brim with carbon, and so that's what I'm going to do here now. I don't really need gloves for this, so we'll go ahead and get our carbon out. Now, I've bought this from Amazon, but again, everything that you see here you can just get from the virtual foundry. I'm not affiliated with them or anything. I just like their product. I think it's very unique to our market, being makers who want to do metal things without having to pour metal. And I'm wearing sandals here, and I'm not worried about metal spilling on my toes. So that's nice. Also, the rapid iteration that you get from direct 3D printing to a metal part is something that you can't really do with casting. Not that I have anything against casting. I actually like it quite a bit. It's just a lot of work to get the negative mold, and then it's one-time use. This is, in this case, you print it as many times as you want, put it in an infinitely usable ballast with, I've used this crucible for, 30 cycles at least, and all you need is pretty basic crafting gear. I mean, a 3D printer, a kiln, and some filament. It's about that simple. So let's go ahead and fill this up to the brim with the carbon. And this carbon is activated charcoal. They use this a lot in water filtration, as well as little capsules that you can take for stomach problems, or if you've been poisoned, food poisoning primarily. So there's a fact for you. But yeah, it's very easy to come by and pretty affordable. With what we're going to do actually after this layer is done is put a lid, which I have over here, which I've also made, but you can use anything that's going to withstand the kiln cycle. Layer of steel. I've even done some copper tape, which is used for electrical components. It's pretty cheap, down to aluminum foil. That works pretty well too, just to cover. But they make some tool steel foil, which you can put on and reuse. So if you don't have access to some refractory or a lid, or didn't go through the virtual foundry, you can still find a way to cover this up to prevent the oxygen. So it's taking a few more scoops than I was thinking. But this can be reused, so I'm not worried about wasting anything. I just want to make sure that this is all covered and does not run out during the 5 hours. I honestly think, based on my previous tests, that probably 3 or 4 scoops would have been enough, but I've bitten myself in the ass before because I thought I was spot on with the measurements and the timings of everything, and ended up putting too little carbon, a couple times, and losing the part. And that's definitely not a fun thing to do. So it's better to be overly zealous with your carbon and not try to outsmart the process. So that's more advice for myself than anyone else. All right, that's looking pretty good. All right, and that pretty much sums up the process. I'm going to be putting this into the kiln after I lay this lid on top. This is exactly how it goes in the kiln. Also, to show the lid, I have a few small holes, which is for the degassing. If I wasn't doing this in a dual... Let's see if I'm saying that right. If I wasn't doing this in a single stage debind and sinter, I would not be using this lid. I would be using a completely solid lid. But what I'm doing is applying this. This will go into the kiln, and in one kiln cycle, that means I hit the button, press start, and then come to it tomorrow and it's done, rather than having to change any settings or apply carbon later. These holes should allow for the degassing that's going to take place during the debind. And debind, again, is near the 400 to 800 degree Fahrenheit mark, which burns off the PLA that the PLA equivalent binder, which is holding together the metal powder, and that'll let that escape. When the temperature reaches high enough for charcoal, or for the coal carbon ignition, that will burn, scavenge any oxygen within this crucible, and protect our part from oxidation. In the kiln, I've also placed a few things on the outside, so I won't show that here right now, but on the outside I have some carbon as well on the outside to scavenge any oxygen from the remaining kiln volume. So anyway, I think I've rambled on enough. This will go into the kiln, and we'll see if this works tomorrow. So thanks for watching.